You've just smashed a pothole at 60 miles an hour. Bang! In that split second, a massive shockwave of force just ripped through your car's suspension. And it all has to be controlled before it, well, tears your car apart. What happens in those few milliseconds is nothing short of an engineering marvel. So let's take a look at what that force actually looks like. Whoa, get a load of this spike. We're talking over 11,000 newtons of force from one pothole. To put that in perspective, that's like dropping a small car, a whole car, right onto your wheel. And it happens in an instant. So where does all that energy actually go? In just, get this, 3,000ths of a second, that massive, violent impact travels along a very specific path. It goes through 8 different components. And that's what we're going to do here. We are going to follow that force step by step on its incredible journey from the road right into the body of the car. Okay, but before we can follow that journey, we've got to meet the key players, right? Because this isn't just a simple spring and a shock absorber we're talking about. No. This is a highly integrated structural system. All right, so here's our map for this journey. First up, you've got the strut itself. This thing is a real workhorse. It connects to the steering knuckle, which, holds the wheel. Then, down below, we've got the lower control arm, which is what anchors everything from side to side. And way up at the top, that's the strut tower. That's the point where this entire assembly bolts right to the car's body. Keep these parts in mind. They're basically our landmarks. Okay, let's start with trial number 1, the vertical load path. This is probably the most common force your suspension deals with. I mean, every single second you're driving. It's the force from the car's own weight just sitting there, and of course, all those constant bumps in the road. All right, now watch this path closely. The force hits the tire's contact patch and immediately shoots up through the wheel hub right into the steering knuckle. Now here's where it gets interesting. The load splits. The main path, the dominant one, goes straight up the strut. That's where the spring compresses and the damper does its magic, turning all that violent motion into simple, harmless heat. The rest of that load, it gets routed to the lower control arm. And then, finally, all of that energy terminates, nice and safely, at the strut tower and the subframe. Now for the next challenge, trial 2, the lateral load path. This is the real test, cornering. The second you turn that steering wheel, you introduce a really powerful side-to-side force, a lateral force that is literally trying to rip the wheel right off the car. So, this lateral force, it also starts at the tire, but it takes a totally different route. Most of it is resisted by that lower control arm, which acts like a big, strong anchor. But think about it. If the bottom is anchored, you've just created a massive lever, right? So what's stopping the whole assembly from just bending in the middle? And that brings us to this really important idea called a bending moment. Basically, that lateral force down at the tire creates a huge lever arm that pushes against the strut. So it's not just compressing the strut anymore, it's actively trying to bend it. This right here is probably the single biggest structural challenge for the entire MacPherson Strut design. And that is exactly why the main tube of the strut is so big and heavy-duty. It's not just some simple housing for the shock absorber fluid inside. It has to be a serious, load-bearing structural pillar. It's engineered specifically to have the strength to fight off those immense bending forces without flexing. So let's pause for a second. We've got vertical forces pushing straight up. We've got lateral forces trying to bend the whole thing sideways. And we know it all has to rotate so you can steer the car. So here's a quick question for you. Which single component has to manage all 3 of those forces? Vertical, lateral, and steering. Did you guess it? It's the strut mount. That's the answer. This little rubber and metal part right at the top of the strut tower has the absolutely enormous job of handling the vertical impacts, resisting all that lateral side loading, and allowing the whole thing to pivot smoothly when you steer. It really is the unsung hero of the entire system. All right, so far we've kind of been looking at these forces as if they're static, not moving. But now let's talk about geometry and kinematics. Let's see how this all behaves when it's actually in motion, because these specific angles we're about to talk about, they are what define how your car actually feels when you drive it. Yeah, these angles you see here, they're basically the secret sauce for vehicle handling. You've got caster angle, that's what gives you that stable, solid feeling on the highway. Then there's kingpin inclination, or SAI. That's the clever bit of geometry that makes your steering wheel want to snap back to center all by itself after you make a turn. And of course, camber. That's all about tilting the tire just right to get the maximum amount of rubber on the road for amazing cornering grip. They all work together in this really delicate balance. Now, here's the crucial part. These angles aren't static. They're not fixed in place. As the suspension moves up and down as it compresses and extends, the geometry actually changes on the fly. We call that camber gain. And engineers use these super complex models, just like this one, to predict exactly how that tire is going to move and tilt, making sure it stays planted on the road no matter what's happening. Okay, so we've seen how this whole system works when everything is going right. But what happens when a part just can't handle the load anymore? What happens when the load path breaks? Let's talk about the breaking point. Remember that strut mount, our unsung hero? Well, this is what it looks like when it fails. The rubber just completely tears apart. And when that happens, that critical link between the suspension and the car's body is totally compromised. You'll probably hear a loud clunking noise over bumps because the entire strut is now just flopping around in there, which means both the vertical and lateral load paths are broken. And check this out. This is what happens when that bending moment we talked about is just too much for the strut to handle. A bent strut, man, that is a catastrophic failure. It'll jam up the damper inside, totally wrecking your ride control. And it throws the wheel alignment so far out of whack that the car can become really unstable and dangerous to drive. But maybe the most dangerous failure of all is when the final destination point for all that force gives way. A strut tower that's rusted through just isn't strong enough anymore to take that load. So under a big impact, like that pothole from the beginning, it can just collapse. And that means a complete loss of control of the vehicle. All right, we've traced the journey of the force, we've seen the ugly failure points. So what's your takeaway? What does all this engineering theory actually mean for you and your car in the real world? Let's connect the dots. So let's bust a few common myths right now. First off, just throwing in some lowering springs doesn't just lower your car. It fundamentally alters all those critical handling angles we just talked about. Second, not all strut mounts are the same. They aren't just a chunk of rubber. Their stiffness is a really critical tuning component. And maybe most important of all, please never forget a strut is not just a shock absorber. It is a structural pillar of the entire suspension. And this is super useful. Here's how you can start diagnosing problems based on what you see, hear, or feel. If you hear a clunking over bumps, that points to a loose connection right at the strut tower interface. Seeing really uneven tire wear? That's a huge clue that your kinematic geometry is off, maybe a bent strut or worn joint. If the car pulls to one side when you brake, that could be an issue with the lower control arm bushings. And if you see oil on the strut body itself, well, that means the damper seal has failed and you've lost vertical load control. Every symptom is a clue. So when you boil it all down, the MacPherson Strut really is a masterpiece of engineering simplification. It does so much with so few parts. But that simplicity demands perfection. It means every single component has to perfectly manage its role in this incredibly complex, high-speed dance of forces. And that just leaves us with one final thought, a question to chew on. Now that you've seen this whole journey, where do you think suspension design goes from here? Is the next big thing going to come from smarter materials, or maybe active electronic control that can actually predict the road ahead? Or will someone come up with a completely new geometry that finally replaces the design that served us so well for more than 70 years? The journey, for sure, continues.